4.6, expressions and equations, pulling it all together. So this one we're going to translate and solve specifically word problems, but they're not going to be structured quite the same as the ones from 4.5. So solving word problems, just like translating from that last section, reading and rereading the problems may have to happen 4, 5, 6, some students 10 times, who knows. But once you feel like you have it, then you can start translating and writing stuff out, you know. But look at the information, just see, you know, what's helpful, especially anything that's numeric. Be careful though, because math people are jerks, and like we've seen in the past, they'll put numbers in there that don't actually mean anything. So we have to be careful. So it may be helpful to always be just knowing what you're trying to figure out what the problem is asking, because like we saw a couple problems ago from that last section, I was solving the wrong problem. Now, it's not like we would have submitted that answer, but we found out that I was solving the wrong problem because I didn't actually know what I was solving for. So sometimes drawing a picture or diagram may be helpful. That happens, yeah. And then what conditions are given? Make sure the conditions are true when checking your work. Like if they say you drove 100 miles more than your pal. Okay, make sure in the end, if you know how many miles you drove and you know how many miles your pal drove, that you're 100 miles more than your pal. You see what I'm saying? Because that's one of the conditions that they gave us. And guess and test. But yeah, guess and test is actually a valid method. Just don't guess and be like, I'm done. Because remember, there's an infinite number of values that can be incorrect. So there's kind of randomly, there's an infinite possibility of getting it wrong. And there's only one out of an infinite number of values that would be correct, usually. So given dirt, D equals RT, D is distance, R is rate, and T is time. This is common enough of a formula, but just to specify, I like to see this written out with the actual words. So it says D, that's distance, equals the R, which is the rate. Now it's rate RT. That means we would be expecting the rate multiplied by the time. Okay, so I just written that out in the words that was given, just so we know if they give us one of these values, which one to expect. So I started working on it before I read the whole thing. See the mistake again. Let's find out if we even need that. So if your friend drives to Moab from your home near Salt Lake City, to Moab, okay, which is about 216 miles, and says it took about 3 hours. Now, we're not worried about the about part. We're just going to say it took exactly 3 hours so that we're not overcomplicating this. But if you'd like to, you're welcome to. I'm just not going to do it. Find how fast your friend would have been going. Now, when it says anything about fast or speed, that is a rate. Now, we haven't gone over rates, which we're seeing a rate right here. Rates generally compare two things at the same time. Miles per hour, dollars per hour, dollars per month. I don't know, some kind of rate where you're comparing two things. In this case, we are comparing miles and hours, but we don't know what the exact speed is. So for us, and I'll use the same letter there, but the R is the value we don't know. Now, I put that in first. It's possible if I would have read the rest of that, right? How fast your friend would have been going. But if you don't understand that the R is the unknown in this case, look at the values that they did give us. For example, up here they say it's going to be 216 miles right there. Okay, well, miles is a distance, so that means you would know to put it in this formula as a distance. I don't really need the label, but the other value that they gave us is time in 3 hours, right? So again, hours, I mean, it does take some knowledge knowing hours is time and miles is distance, but the time is definitely going to be 3 hours. So 216 equals, again, now we know that the rate is the value that we don't know. The rate times the time, 3. Now, if you feel more comfortable writing this out as 216 equals, instead of R times 3, you could make it just 3R. But the truth is you don't necessarily have to do that, because Remember our principles of equality. We are solving for r here. And so we're at the point where we're at a one-step equation. One principle of equality to solve this. So if you were to see this multiplication, we should know that we are trying to make a 1. Because multiplication and division is how we make 1s. So I would say this principle of equality right here, I would want 1r. And some people would say, oh, there's a phantom 1 there. That's true, but it's actually being multiplied by 3. This 3 is the coefficient. It's just on the wrong side. So again, if you like to write it like this, then you're welcome to do that. But at this point, I would say that 3, I'm going to show it differently. I'm going to show the division with a fraction line. And then, well, I guess I'll show it with the fraction line over here as well. So now, in order to figure out the rate, which is going to be in miles per hour, there's 216 miles for 3 hours. What we want is a unit rate for 1 hour, which is why we're going to divide these. So I'm going to do the division over here. 216 divided by the 3. Okay, 3 won't go into 2, but it will go into 21 7 times. 7 times 3 is 21. So that's going to zero that out, drop the 6. 3 goes into 6 twice. 2 times 3 is 6, nothing remaining. So our quotient there, that's a 0, by the way, not a decimal. 72. Now going from Moab to Salt Lake City, is that fast? I mean, not on the freeway. But, you know, if you go through Price, I'd say that's kind of faster through those roads. Maybe you get a ticket. But if your friend did in 3 hours, probably didn't get a ticket either. Now, the answer is not 72, though. So the answer is not 72 because this is a word problem. We need a label to go with the 72. Well, remember, it was 216, it was miles, so that'd be 72 miles. And then we would make it per, I'm going to show it as a fraction there, but per hour. I don't know, maybe 72 mph would be better. And miles per hour, whatever. It's all the same thing. The first 4 stages of a pattern are shown in the diagram below. If the pattern continues, how many red boxes will there be in stage 10 of the pattern? Write an expression for the number of red boxes in stage n of the pattern. So this one is, it's not an equation because it doesn't have an equal sign. We can show the expression as well. Again, it's kind of just a formula for this. But how many boxes will there be in stage 10 of the pattern? So just to start out, we can count how many red, oh crap. All right, so the first one, you can count them. I counted 6. The next one, 10, then 14, and then 18. Okay, so the pattern that I see here between each of the stages, this is stage 1, stage 2, stage 3, is that each of them is adding 4. So, for example, you do 6 plus 4 to get your 10, 10 plus 4 to get your 14, 14 plus 4 to get 18. Now, I don't want to do this 10 times either, right? So what I can do is just say, well, there's actually several different ways to do this. Now, I'm not going to draw this, not because my drawing sucks, because I'm actually too lazy to draw it. But stage 5, so let's do that. Okay, so we got stage 4 has 18 red squares there. We're going to add 4 to it because we know we're just adding 4 each time. And that will tell me how many boxes that would be red would be in stage 5. 18 plus 4, boom, 22. All right, now here is something that happens from time to time. We want stage 10, and we say, look, here, we got stage 5, and now we can scale this, right? So if we scaled it, that means we're just going to multiply this by 2 to get stage 10, and then we'd multiply this by 2. I'm not going to do the math, but it'd be 44. There's a reason why this doesn't work. We just haven't done enough work to really explain why it doesn't work. But I'll say this, is if there were, and this is where it kind of gets a little important there, if there were a stage 0, in order for this to scale like we did, you would have to multiply, you would have to have 0. You'd have to have a 0 here as well. But that doesn't fit the pattern, because then you'd have to add 6 to get to this 6, and then you'd have to add 6 every time. But we can see we're adding 4 every time. Okay, now, again, I'm not fully explaining why you need 0 squares there. But let's take this, what we have. Okay, so again, let's take that same idea of scaling. So again, we know that 0 there doesn't work. We could scale with the 2 as well, right? We could come up here and be like, okay, I'm going to scale the 2. If that were the case, then I would multiply the 2 by the 5 to get stage 10. And then I'd multiply the 10 by 5 to get 50. But again, the answer is not 50. But you can see at least we got 2 different answers. If we scaled this value, then we had 44. When we scaled these values, we got 50. Very different answers. Yeah. So we can't do that. We cannot scale those unless, the only reason we could scale those is if we had no red boxes in stage 0. One thing that we will want to notice on this, that we're adding 4 every time, right? Yeah. So I guess I'm kind of jumping to part B here because maybe it'd be helpful. But if we see that we're adding 4 every time, add 4, add 4, add 4, add 4, that's repeated addition. So what I could do is just, instead of using repeated addition, just change that to multiplication, right? So what we could do is we could say, you know what, I know that I'm just going to multiply by 4, and I'm doing it down here at the bottom because I don't really care what stage I'm in, right? All right, so if I do this for stage 10, so I'm going to add 4 every time. I'm going to do this how many times? Stage 10, right? Stage 10. Now that would be 40. Now there's not 40 in stage 10, but I'm just kind of trying to get us there, right? Okay, so these 40, what would these 40 represent? Well, think about it like this. If you were to do stage 1, right? So that would be, let's go to stage 1 there. That'd be like you got 4, and well, you'd have 4 times the 1 there, and that's 4, right? Now there's 6 red boxes, so that means that 4 you'd have to add 2 in order to get the 6. Now I added these 2 arbitrarily just because I know 4 plus 2 is 6, and I know that there's 6 red boxes. The question is, where are those 2 red boxes? Well, let's see. Before we answer that, let's go to the next part. So let's go to the stage 2. So again, stage 2 would be, since it's repeated addition, we know we're going to take 4 and multiply it by 2. Now that's going to be 8. That's going to be 8. But again, I see that there's actually 10 total red boxes. So I would have to add 2 to that to get 10. Okay, so we're seeing another consistent pattern here, aren't we? Yeah. After the multiplication, we add 2, don't we? So let's see if it works for all of them. So 4 times 3, that'd be 12. There's, in stage 3, there's 14 red boxes. So again, we see the add 2 thing to get 14 red boxes. All right, that's looking pretty good. What about 4? Stage 4, well, 4 times 4 is 16. We're still 2 away from 18, so we'd need to add 2 boxes, 2 more red boxes to get 18 red boxes. Now let's just double check with the one we found. 4 times 5 is, that'd be 20 of those boxes. We're still 2 away from 22, so it's 22. Okay, so in this string of finding values, which is really going to help us to figure out the expression as well, we're adding 4 every time, which is where this multiply by 4 thing comes in. But we notice in each of these cases that we're adding 2 as well. So you do the multiplication, which we did right here, and then after the multiplication, you simply add 2. Boom, you get 42 red boxes in stage 10. 42 red boxes. Now that's nice, and maybe we wouldn't have noticed that, but here's the thing, is where does the plus 2s that we got in here, all these plus 2s, even this one, in the boxes, in the diagram, in the picture, where are the 2 boxes? I would also say that these are the 2 middle ones right here, because, look, you got, remember this was 1 times 4, right? 4, 1, 2, 3, 4. Okay, 4 times 2, 2, 4, 6, 8, then the 2 in the middle. This one, 4 times 3, 12, 3, 6, 8, oh, suck. Let me try that again. I did just, oh man, here we go. 3, 6, 9, 12, all right. Sal does know his multiplication tables sometimes. Okay, but there's the 12, there's the 2 in the middle, right? 12 plus the 2 in the middle. How about this one? 4, 8, I'm taking my time, 12, 16. Okay, so there's the 16, 2 in the middle, boom. So when we're adding these two, there was these 2 in the middle that were just always there, right? And then I would say these, I don't know, I'm starting to think of spider legs, but whatever. You know, they're just these legs that are just growing out from the middle right here. And that, just to go back, that means that stage 0, this is significant. It's just not significant now, but stage 0 has 2 boxes. It would have been the 2 middle ones right there. So in the next part, it says write an expression for the number of boxes in stage n of the pattern. Okay, well, stage n, again, we can see that all we're doing is taking 4 and multiplying it by the stage there. So this one just happens to be stage n. We don't know what that number is. But after we multiply by 4, that tells us how many red boxes are branching out from the middle, and then the middle has the 2 red boxes. That's it. That's it. So we got that answer. Stage 10 has 42 red boxes, and then the expression would be something like this. So now that we have the expression, and it didn't ask for this, but if it said, you know what, how many red boxes would be in stage 100? Because I don't want to draw that crap. But it'd do 4 times 100, 400 plus 2, 402, boom. Could you do 70? Sure you could. You could do 70, you could do 1,000,000, you could do, I don't know, stage -10, I don't know, whatever. But this expression now becomes a formula for this diagram. There we go. All right, more words. I will read this one. According to the Bureau of Labor Statistics, I mean, what kind of person you got to be to look at that garbage? An automotive service technician earned a median pay of $16 per hour in 2012. Don't worry about the median thing, although it is a math thing. Let T be the number of hours worked at the rate as an auto service technician. A, fill in the following table showing the arithmetic expression used to calculate the gross earnings for working a certain number of hours. B, using the pattern, write an expression for the total gross earnings in terms of T, the number of hours worked. So gross earnings would equal, and we'll fill in that blank. If you want to figure out how much the technician made after 28 hours, you would use the number T equals blank. D, using parts B and C, determine how much the technician makes after working 28 hours. And then E, extend the table or create a formula to find the number of hours needed to work to gross $256. We will do it, but first, let's identify some important values, such as, it doesn't look like the year 2012 is particularly important because down here is just number of hours worked. So nothing to do about the years. And I don't know how accurate this is either. But what it does say is that the technician, automotive service technician, will make $16 every hour or per hour. It's the same thing. So in my table, we got number of hours worked. If this technician works exactly 0 hours, how much will they gross earn? Now, with that though, sometimes in the problem they'll be like, they make $16 per hour, but they get like a $500 signing bonus or something like that. Okay, then if they work 0 hours, they get that $500. And again, this is assuming there's no stipulations with it. But in this case, if they work 0 hours, they will get paid exactly $0. Now, what if they work exactly 1 hour, which is the next row? Well, we know that then they would make their first $16 because every 1 hour, they're going to make $16. That's what it says right here. So if they work 2 hours, what you can do, there's 2 ways to do this. You can take the 16 and add another 16 right there. So 6 plus 6 is 2, carry the 1. 1 plus 1 plus 1 is 32. They'd get $32. Or if you wanted to, you could do $16 an hour for 2 hours. 16 times 2, which is still going to be 32. So the next one as well, you could do 32, but another $16 for the next hour, the third hour there. So that's 2 plus 6, which is 8. 3 plus 1 is 4. But again, if you'd like to, you can do $16 an hour for 3 hours. It's the same thing. In a table like this, it's actually doesn't matter, right? Well, we filled out the table. I guess I forgot to check if that's, yeah, fill in the following table. Okay, so we did it. Okay, so part B, using the pattern, write an expression for the total gross earnings in terms of T, the number of hours worked. Now, what you would not want to do right here, because we were doing the addition thing, right, is you would not want to do something like 16 plus 16 plus 16. And the reason why you don't want to do that is because we don't know how many hours are going to be worked. So we don't want to do that. What we do want to do is, this is where the addition, I mean, it's nice, repeated addition, but again, since we don't know how many times it's going to add to itself, we're going to have to use the multiplication on this. So the gross earnings, I know that it's $16 every hour, so I got my 16, but that would be just for 1 hour if I kept it there. Since we don't know how many hours are going to be worked, I can just multiply by T there in terms of T. T is the number of hours worked, so 16 times T will get us the gross earnings. Right, like this one, even this one, if they work 0 hours, well, 16 times 0 is $0 gross earnings. 16 times 1, $16 for that first hour, 16 times 2, 32, 16 times 3, 48, and so forth. But that at least is the expression or the formula that you would use for number of hours worked for this automotive service technician. If you want to figure out how much the technician made after 28 hours, you would use the number T equals, that's our T for time in this expression, or I can call it an equation, but 28 hours instead of T. So 28 here. I'll label it, what the heck. Okay, so with that, using parts B and C, determine how much the technician makes after 28 hours. Okay, well, the formula is showing 16 times T, but part C says instead of a T, we know how much hours they're going to work, 28. When we get this, that will tell us how much money the technician would make after 28 hours of work. Well, I have that lined up horizontally, but we're going to have to multiply with stacked multiplication. So let's do that. All right, multiply. So first up, 6 times 8 is 48, carry the 4. 8 times 1 is 8, but adding 4 would make that 12. Okay, now the tens place value, so no ones. But 2 times 6 is 12, so carry that 1. 2 times 1 is 2, but adding the 1 would be 3. Yeah, thank you. It's hard. It definitely is after, I guess, this much time for me anyways.
It's Thursday.
On some days. So in the ones place value, 8 plus 0 is 8. In the tens place value, 2 plus 2 is 4. In the hundreds place value, 1 plus 3 is 4 as well. So the technician would make $448 in dollars. We're not looking at tax because we haven't done decimals yet, but we like to keep this positive, even though we kind of just finished the negatives unit. So extend the table or create a formula to find the number of hours needed to work to gross $256. Okay, so let's take this. I'm going to write here on the left. The formula is 16T, and that would equal the gross earnings. Well, here it's saying your gross earnings is going to be 256. So instead of gross earnings, we now know what that value is going to be. So I kind of went from an expression into an equation down here because they now have told us how much that's going to be. Now, I'm not going to put the decimal on there, not just because we haven't gone over decimals, but because it's more writing than I want to do again. So we're going to go into principles of equality now. Oh, yeah, I haven't used orange. So we want 1 T, not 16 T's. So we're going to take the 16 and divide it by itself. If I do it to one side, I must do it to the other side. All right, so some long division, which we love so much. So we got 256. And we're going to divide this by 16. Okay, so we're going to need some multiples of 16. I'm going to make a table here on the right of that. So, of course, we're going to have 16 plus another 16 would be 32. I'll skip some of the math there. Plus another 16, it's going to be my third multiple, 48. Plus another 16. 64. I'll do one more. Plus another 16. Appears to be 80. Oh, so that's kind of small. Yeah. All right. So let's proceed then. So 16, it will not go into 2. But it will go into 25 once. 1 times 16 is 16. Subtract. So we'll make that 15 minus 6, which is 9. And then we'll drop the other 6 there. So I'm going to need another 16 in my multiples. And in fact, when I do, add that next 16, boom, 96. So that right there is the 6th multiple of 18. I said 18, I meant 16. 6 times 16 is going to be 96. When we subtract that out, nothing remaining. So the quotient here on the left is 16. But it's not 16, because it's a word problem. We do need the label, 16 hours. That's it. Your family has 2 cats, Zeus and Athena. Together they weigh 14 pounds. Zeus weighs 4 pounds less than Athena. How much does Athena weigh? Right, solve an algebraic equation to represent the situation. Use A to represent Athena's weight. Okay, so it says up here, it's going to say that together they're going to weigh 14 pounds. So that means you got the 2 cats. We got Zeus. And we got Athena. Like this, the 2 cats. Together means we're going to add the 2 values together. They're 2 weights, and this would be a total weight, I guess. Okay, well, it says that Zeus weighs 4 pounds less than Athena. Okay, I guess maybe I was writing the wrong equation. Because we don't know how much they weigh total, right? No, I didn't say that. Okay. No, it did. It did. It did. So, together, that's the total weight. It's going to be 14 pounds. Boom. I'm going to put that in. So that's what we underline. We're going to add those together. Let's see. Zeus weighs 4 pounds less than Athena. So we've got, here we've got another Athena for Zeus. So, but Zeus, it's going to be 4 pounds less than Athena. So that means you'd have to take Athena's weight. I'm using a capital A because my lowercase a's are pretty horrible. And then it's less than, so that's a minus. And it was 4 pounds, right? And then Athena, just by herself, weighs the A pounds. We don't know how many pounds that is. This is the equation that I'm going to use. Since this is the equation, that would be our first answer. That's right. The algebraic equation. I'm using capital A's, but it should be lowercase. Now I'm ready to combine like terms, which I have. A and A. That's in one A and another A. How many A's is that? That's 2 A's. In fact, it's positive 2 A's because I'm going to bring the negative 4 down directly right here. And then this would equal 14. Needing more space. So now we're gonna use some principles of equality because there's no combining like terms anymore. I'd like to take the 2 A's and just drop them like this. So I don't want that negative 4 there. I'm gonna have to add 4 to both sides. Okay, so negative 4 plus 4 is 0 as planned. We've dropped the 2 A's, and then on the right side, 14 plus 4 is gonna be 18. The last thing we need is to get 1A. That's, so right now, if you had, we can interpret this. If you had 2 Athena cats, it would be a total of 18 pounds. We only want 1 Athena cat, and so this goes back to kind of why the principles of equality work. But I would divide both sides by 2 because I don't want 2 Athena cats. I only want 1. Well, maybe you want 2, but whatever. 18 divided by 2, 9. So 9 pounds. How much does Athena weigh? 9 pounds. And even with this, we can figure out how much Zeus weighs. So if Athena weighs 9 pounds, Zeus is 4 less than that. So 9 minus 4, boom, 5 pounds for Zeus. We didn't need it, but you could. A student doing a chemistry experiment has a beaker that contains 75 milliliters of an alcohol and water solution. The lab directions indicate that there is 4 times as much water as alcohol in the solution. How many milliliters of alcohol are in the solution, and then how many milliliters of water are in the solution. From this, we got 2 things that are in this beaker, and we know how much is in the beaker as well. So we're going to put 2 things in the beaker. First, we're going to look at alcohol. And yes, I have to check just to make sure I'm spelling it right. We got alcohol, and then water. I can usually spell that on my own, but not always. Okay, so alcohol and water that are in the container, beaker. Okay, so this would be total amount of mixture, solution. Okay, whatever. So if you were to take those 2, alcohol and water, and add them together, you would have the total amount of solution. And in the problem, they say that it's going to have a total of 75 milliliters of solution, alcohol and water solution. So that 75 goes where the total is, right there. So we know that's what it's going to equal. And at this point, it says the lab directions indicate that there are 4 times as much water as alcohol. So I would translate that, not that you have to, but that's 4 times as much water. So 4 times as much alcohol. I read that wrong. 4 times as much water as alcohol. So yeah, you'd have to take 4 times the alcohol. That's how much water you're going to have. Okay, so water is going to be the same as this 4 alcohol over here. So I'm not going to put a W in there. And then the A for the actual alcohol content. So this becomes the equation for us to solve. We're going to make that 1A plus 4 A's. So that's going to be total A's, 1 plus 4. 5 A's. That's going to equal to 75 milliliters. So if you took 5 parts alcohol, you'd have 75 milliliters. Now divide both sides. This is for A by 5. So skipping some of that long division there, A, 15 milliliters. So alcohol content in this beaker, 15 milliliters. And then for the alcohol or the water solution, we're going to take the total amount, which was 75. And we're just going to take away the alcohol content. So that'd be 60 milliliters of water. Or you could have done 4 times the 15 to get the water content, and that's still going to be 60. The sum of 3 voltages in a circuit is 50 volts. The middle-sized one is 4 volts more than the smallest. The largest is 10 more than the smallest. What is the value of each voltage? Write a linear equation that will help you solve this application problem. Use the variable S for smallest voltage, which is nice because we have 3 different voltages going on. We have the smallest voltage. And I'll need some space here, so let's not do that. Let's go back and move this over. So I'm going to say, because they told us to, that S is the smallest voltage. Smallest. Then they got a medium-sized one, so M, well, I'll just say medium. You know what? Let's make that, let's try the color code this. So I'll make M medium in red. And then we also have a large one. The good news for us is that all three of these are written in terms of the smallest one. So our medium one, the middle, I said medium, middle is 4 more than the smallest. So again, doesn't matter how you write that, but I would take the smallest one and then it's 4 more than that, so add 4. And then we got the largest one. The largest is 10 more than the smallest. So again, my large is going to be the smallest, but we're going to add 10 to it. So that's the expression that I get for all three voltages. So let's see if we can write the equation. So I'm going to do it like this, and it doesn't necessarily have to be in this order, but I'm going to take my smallest one, so the smallest, and then we're going to compare it to, I said medium, but I'll put middle here. There's 1, 2, and then 3 is the large one. I can spell large. And we will compare this with a total voltage. All right, now we don't have to assign operations yet, but I do know that I'm going to add them. So I'm going to add them. There we go. So the smallest, well, we know that the smallest is just S for smallest. The middle one, you could put M right there, but we don't want 2 variables. We want only 1 variable in the expression, and the middle one is showing the smallest one, but 4 more than it. And then the large one, still compared to the smallest one, but it's 10 more than it as well. So if we add these together, we should get the total voltage, which up here they said you get a total voltage of 50 volts. So we'll put a 50 in there. That is our equation. So that's the linear equation that they want us to solve. Well, let's go ahead and solve it then. So I would combine, I got 1, 2, 3 S's, 2 combined, 1, 2, 3, 3 S's. And then I've got also a 4 plus a 10, which is going to be positive 14. So this equals 50. Now, principles of equality. So first up, let's get rid of that 14. So minus 14 on both sides. That'll zero that out. We can drop the 3 small voltages, which is going to equal 50 minus 14. So we'll make that a 10. 10 minus 4 is 6. 4 minus 1 is 3. And then last of all, for my small voltage, I'll divide both sides by 3. So that's 1S, which was part of the plan. 36 divided by 3 is 12. 12V for voltage. What was the question? What was the value of each voltage? Okay, the smallest voltage we now know is 12 volts. The medium one is, so we're going back up here, is small plus 4. So that would be then, that's going to be 12 plus 4. Which is 16 volts. So middle is 16 volts. And we got a large one. So once again here at the top right, all right, we got the small voltage, which is 12. We need to add 10 to that though, because it's 10 more, 22 volts. 22 volts. Now again, we should check 22 plus 16, that'd be 38, plus 12, 50 volts. So it does satisfy that condition, and we did it. There's the objective. I can translate and solve word problems, and we had so much fun doing it.